All right, so in this video lecture right here, allow me to start getting you into, to walk you into that unlimited world of application of exponential functions right here. Okay, and so in my style of teaching, I always teach this at the very end after you have learned all about the different exponential functions. And after you have been fluent and introduced and become fluent with all logarithms, and all of the ideas about logarithms and as well as logarithmic properties and logarithmic functions. Yeah. So and then here in this particular lecture, this is where we bring all of those. I will bring out, this is where you will see how exponential functions exist in your daily life like that. And along the way, as a way to solve a lot of exponential function problems right here, there will be the log operations that come along right here. So this is really the title of the discussion topic here is the applications of exponential functions. But there are a lot of work that requires the use of logarithms in a lot of these problems right here. And so this is it's not only just applications of exponential function, but really there's always a logarithms behind the scene in a lot of these works as well. Okay, so in the way how I just now introduced it, then definitely require that you must view this lesson here. Anyone learning this lesson must be learning it after you have learned about what an exponential is, be fluent with an exponential function, have enough understanding of what an exponential function and enough understanding of what a logarithmic function is. Okay, and all of the basic properties, all of the properties of logarithms, so that we can work fluently with this particular lecture over here. And so, aside from what I was mentioning about the prerequisites for this particular lecture, now allow me to change my style of teaching a little bit in this. So here in this way, how I approach it, allow me to start out with. So I will shortly right after this, I am going to immediately introduce 5 problems that represent a lot of problems out there in the world. And then throughout the entire lecture here, all of my explanation and all of my work will focus and will be circulating around these 5 problems that I'm about to quickly put it up on the screen right here. Okay, so all right, so these are the 5 problems that I've been collected throughout my years of teaching right here that represents enough, these are representative enough to the real world applications out there where we see the existence of exponential functions. Okay, and right here, and in a way how I was saying earlier in my style here, I only bring up these problems as problems, but really none of these, if you're having a closer look, none of these problems here has a question. So these are just simply problems being brought to our attention. So just think about this problem number 1 right here. For example, this could be a well-known problem among the socio-economic experts where they measure the growth of a population. Okay, so in the wording of the problem itself, I came up with this country right here. It's called a utopia. Okay, it may be a real country or it may not, but it represents the idea that somebody is studying, some professionals out there are studying the population, how a population is growing or changing. Okay, so the population of utopia was 25 million in. I had a typo right here, but this needs to be in the year 2000. Okay. So the population of utopia was 25 million in 2000 and has been growing by 4.5 each year. Okay, and so back to what I said earlier, this problem, I didn't even have a question for that, but it's aside from this question, generally it brings up the idea that there are a lot of professionals out there who want to study the growth of the population. Okay, the growth of the population. Or even more generally, the change in the size of a population. Okay, and most ultimately, a population itself is a quantity. So if this is a country, then it's a quantity of people. Okay, And then let's now quickly look into the next problem right there. And I did not bring in any of the questions in here. So problem number 2, the population of a certain bacteria that started out with 11,000 of them initially, okay, and doubles each hour. So think about it. Aside from this problem, generally there are many other problems where the scientists are interested in knowing. The biologists, or more specifically, or more the biologists, or specifically the people who are more interested in this kind of problem like that. Okay, and then that's how it works out there. Okay, here in problem number 2 that I put on the screen earlier, then a population also represents a quantity, and so this quantity here is the population of some kind of bacteria. Okay, and so now we can see that just right here, according to the description of the problem that the scientists, the biologists are studying, then the population of a certain bacteria, well, this number, we will talk about that a little more, but it's in the way how it is. It doubles each hour. So think about it. Again, it's bringing up the idea that there are professionals who study the change in the size of a quantity. So the quantity of, in that problem number 2 right here, is the quantity of the amount of bacteria. And so over time, see, the description was saying that population doubles each hour. Okay, and so over a certain amount of time, it's going to grow bigger and bigger. It's going to get to some larger size. And we will get into, and we will see how we can work with that and come up with functions that model and help us estimate the future amount, the future value of those populations in a certain amount of time later. Okay, so let's head on to the next problems right here that I can briefly introduce. And by the way, along the way that I'm explaining here, feel free to take a screenshot of at any instance of when I'm keeping these 5 problems on the board right here, so that or on a computer right here, so that you can always have a copy of these 5 problems to always reference back. Okay, and so now problem number 3 right here is a very realistic problem that happens to a lot of us. $4,000 is invested in a bank account in a bank account at an interest rate of 7% per year, or sometimes people say 7% annually. Why did I say this problem is for almost every one of us? Because at some point in our life we'll start thinking, at least when it comes to being when it comes to time being a parent, okay, then you start thinking about making investment to grow your financial budget, so that you can later on support your kids going to college. So the idea now, you're gonna put out an amount of money and send it to a bank, okay, and once you send it to a bank right here, the bank is gonna, basically the idea is the bank is going to borrow your money for that, and then the bank pays you interest. Okay, and so there's that interest rate right here. So the idea is that you're making money by lending it to the bank right there. The bank, upon borrowing your money, the bank is gonna reward you with the money that produced on its own. So the interest rate here is indicating the amount of money awarded back to you by about 7% per year. So think about, if you have $4,000 at start, bring it to a bank, hand it to the cashier there, or the bank teller there, and then the bank person say, hey, so in the next year right here, you're gonna earn, so a year from now, you're gonna earn, according to the description, a year from now, you're gonna earn 7% of what you brought in today. Okay, and so if we leave that for 18 years, 20 years, that amount definitely will grow to something big. Okay, and that's the basic idea about for anyone who's opening a saving account. Okay, not only just the one who's doing parental work, but college students, you need to also save, do some kind of saving to afford college costs and all that. Okay, so like I said, that problem number 3 I brought up is another problem where it's indicating, we have a quantity that it will grow, or it will definitely change its size over time right there. And we will be learning how we can use specifically exponential function to model that function, to come up with a prediction, to come up with an estimate about in how many years we're going to reach this amount, or in this many years, how much amount we're gonna get. All right, and so now it looks like the first three problems brought up the idea right here from the wording of the problem, right here from the worded description of the problem. It looks like the first three problems mainly talked about a population, a quantity that's growing over time, getting bigger and bigger over time. But now if we're looking even closer, okay, problem number 4 and problem number 5 right here, these are the kind of problem where, so let's now have a look at problem 4 then. 10 milligrams of bismuth, 210 isotopes. I don't have to be a chemist expert right here, but we hear this term daily enough. It's an isotope. It's some kind of, think about it, it's some kind of chemical the element. Okay, and this problem is a problem where the chemist, the chemical scientist, are a lot of times working with. Okay, and a lot of the chemists are interested in this kind of problem right here. So we think about, initially we start out with 10 milligrams of bismuth 210, whatever that is. Okay, 10 milligrams of bismuth 210 isotopes. But then see, it reduces. Okay, it reduces about 13% each day. So right here now, admittedly, I am not using the very formal term for this. Okay, by using the word reduces. Okay, and later on I will use a better term for that. But 10 milligrams of bismuth 210 isotope reduces about 13% each day. The idea is that for a lot of chemicals, it's just the way how nature is, and that's why it fascinates the scientist to study the nature. Okay, so chemists, the scientists who study about chemicals, they found out, they discovered long ago that these chemical properties, these chemicals that we have in our life here, they just naturally on their own just disappearing and disappearing. Okay, another way of saying they break down and disappear. Okay, and so that is the reason why, one day any one of us pass away. One day any one of us pass away, and so when a living organism passes away or dies away, the body breaks down and disappears over time. Okay, so right at the day that the organism dies, okay, whatever the mass that's there, 1,000 years later, million years later, there's only tiny amount, but it's a natural process that no one can escape from it. Okay, and so, but I want to emphasize on problem 4 here in the fact that the population itself, the quantity is so unlike problem 1, 2, 3. The problem number 4 right here is introducing the kind of problem where the quantity is changing in the reducing way. This is where the wording is making it clear right there. Okay, so we are reducing itself. The population itself is reducing it. Okay, and so now, and just like that, there is also, if you don't like working with chemical substances, there are also other problems out there where we can see that a quantity reduced on its own right here. A vehicle purchased for 32,500 depreciates at a constant rate of 5% each year. So now there is another reality that maybe a lot of us know already, but there's maybe still some people who are not aware of that. We bought a car. And then over time that car is losing its own value. So right at the time we took it out of the dealership, took it out from the dealer, 32,500. Okay, we spent a lot of money for that, but over time the car is losing its own value. Okay, and you see in daily life there's like the Kelly Blue Book to help you determine the price. Okay, so the problem I put here is sort of like a theoretical problem, but it's indicating that there are quantities out there. It's generalizing a fact that there are quantities out there that's losing its own. Okay, that's reducing its own right here. That's changing its size, but in the reduction way. All right, so 5 problems here already represents a lot of many other problems here where eventually I'm going to point out this is all where we can use the exponential functions to model, to come up with a prediction of, hey, like say in what year or in how many years the population of Utopia will double of how it was there initially, okay? Or what would be the amount of, what would be the population of in Utopia in 25 years later? Because the problem started out in 2000, so in year 2025, okay? Then how big is that population? How big would be that population? We can come up with a way to estimate that. All right, and so now that's how I just, with the 5 problems here, I really want to emphasize that this introduces you to the to the realization how exponential functions really exist out there. There's a whole reason why we've learned about all of these in the earlier lecture about exponential function, because there are an unlimited amount of applications out there that focus that exponential functions apply to. All right, so let's get to it. Let's really get to working right here. So throughout what I've been saying, the 5 problems, there's one common thing right here. All right, so this is one common thing I've recognized throughout the 5 problems I brought up. And feel free to pause the video and roll back to the notes that you took, the screenshot that you took about the 5 problems to convince yourself what I'm saying here is correct. So we have a quantity. Okay, so in any of these problems right here, there's a quantity. There's a quantity is changing. Okay. Or I shouldn't say A, I should say the quantity in each problem is changing. Okay. The quantity that's studied in the problem. All right, so this is easy enough. Needless to say, the quantity that is studied in the problem is changing. Well, the population of Utopia, that's the quantity. It's changing, and we know it's have some starting out amount, and then it's over time it's going to become something else different. Okay, the population of bacteria in problem number 2. Okay. And so that's the quantity is changing. And see, it started out with 11,000. So go ahead and look at that problem number 2 if you have a chance to. Okay, the population of bacteria started out with 11,000, and it's changing. It's doubling each hour. That population is doubling each hour. Okay. And then so, after realizing that in any of those problems and in any of those other problems outside of these 5 problems, there will always be a quantity that is changing, the quantity that we study in that specific problem. There's a quantity that's changing. Okay? And then there's an initial there's always an initial amount. Okay, there's an initial amount. Underline this for me. An initial amount at starts. Okay, there's always an initial amount at starts. All right, and then for each problem, so say right here, see the population of Utopia was 25 million. This is the initial amount here. Okay, and that starts. We're starting at the year 2000 right here, and then the population of bacteria, see, started with 11,000 of them initially. This is an initial. I can call this the initial amount. So the initial amount for this Utopia population problem is here 25 million. This initial amount is right here. Okay, for the population of bacteria, whatever bacteria that is. Okay. And so with this banking problem, with this investment problem right here, 4,000 is invested in a bank, okay, in a bank account at an interest rate of 7% per year. This is that initial amount. because we're initially starting out with 4,000, and then once we invest that, once we have invested that into a bank, it's going to grow on its own depending on the formula that the bank is giving us, okay, is offering us, okay. And so once again, so my point here, and needless to keep going through the rest of them, you will see it all in there. So that's why I said this is one thing common in any of these problems. There's always an initial amount. The quantity itself is changing, but there will always be an initial amount. Now, I'm not saying that the initial amount is always known in our problem, okay? But there will have to be an initial amount, okay? So sometimes it will also be. I will also bring you into an example where we have we know the modeling function, but we don't know how large that initial amount was, okay? But there will be an initial amount. It's just whether we know it or not. That's where we have to do some math work sometimes. All right, and so the next thing I want to point out over here. So the quantity itself is changing. Okay, so now the changing can be grow or reduce, right? Or how about the quantity is growing or reducing, okay, at a rate, okay, that's a rate, a proportion, okay, growing or reducing at a rate, at a rate that a proportion that's related to the initial amount right there. Okay, and so let me point out what that is. And so $4,000 is invested in a bank account, right? At an interest rate of see, this is a rate for financial math. People in financial business, in financial math, people doing financial math refer to this as interest rate, 7% per year. Okay, so it's a rate, and this rate right here indicating how fast our money is growing. So this is a growing problem. Our amount, our quantity is growing. So 400 will become bigger later, but at a rate of 7% per year. All right, and so this problem number 2 right here. The rate is not very clearly seen in this problem, but there is clue again that there are clues in here, or there is clue in here that leads to there is a known rate. So this population of bacteria started out with 11,000 of them initially, and doubles each hour. Double each hour. Doubling each hour means really means from the initial one, for the next one, it's going to be another way of saying, how about, so doubling, okay, really means the same as increase, okay, increases or grows, the quantity increases or grows by 100%. So according to the problem of that, according to the definition, to the wording description of that problem, and then in every hour, in each hour later, in each 1 hour later, that population of bacteria grows by 100%. That means if we're starting out with 11,000, right? An hour later, there are 22,000. That means there's 100% of those that's produces and added back to the beginning one. All right, and I will even get more deeply into the math later, but I just want to say, the key word here is doubling. So it's kind of hiding away the rate of the rate of growing or reducing. But the truth here is behind that scene. The truth behind the scene is that when it's say doubling or tripling, there's always a rate of behind the scene. There's a rate of change behind the scene right here. So with the population there in problem number 2. Increases or grows by 100%. That's another way of saying it's doubling in every hour. Okay, and so just a little extra for anyone learning from this lesson, but see, tripling. Okay, so tripling. So tripling would means we increase. So we increases or grows by 200%. Okay, increases by or grows by 200%. That's what tripling is for. All right, and so that's some explanation about the wording. So in any of the problem, there has to be there has to be some clue about the growing or the reducing of the amount. Right, there has to follow a certain rate. Okay, the certain rate of the preceding time. Okay, of the preceding time period. All right, and then allow me to bring in some more the common the thing that we recognize throughout these 5 problems right here. Okay, and so the rate is the rate is simply just a proportion. Okay, so this is not anything new. It's just right according from what I have been explaining. So the rate is just a proportion of the quantity. Okay, of the quantity. In the previous periods. Okay, in a previous period of the time before that. So here right now, allow me to talk about. See, some of those are looking in per year. So each year is a period. Some of the other problem is talking about the per hour. So each hour is a unit or is a period of time right here. Or the per month or per day, each day, right? So the rate is a proportion of the quantity in the previous the periods. Okay, and then I should have added more clarification for this, but the rate here is how about a constant rate? Okay, and that's good enough for us. It's a constant rate. All right, double underline that. All right, so these are some of the major characteristics. Okay, some major characteristics of these problems here. All right, so now once we have recognized these common characteristics right from the 5 problems, and so the point now is that once I have given out these 5 problems right here, the outside of these problems there are limited. Like I said earlier, there's a limitless world of applications out there. But as long as you recognize these 5 major characteristics in any of your problem, then very high chance that your problem there has an exponential grow or an exponential. Later on, we're going to call it a decay, but I'll get to that. Okay, so again, as long as we can recognize these, indeed there are only 4 major characteristics here, but once we've recognized these major characteristics in any of the problem outside of these 5 problems I introduced, then very likely that the problem you're working with has an exponential functions behind the scene to model the quantity that you're working with. Okay, and once you're done right here, student learning in this class is still early in your mathematical development right here. So you may end up going into engineering. You may end up applying your math into science field. You may end up applying your math into financial math. There are so many ways out there. But once you get to doing your work and start working with the exponential functions, look for these 4 major characteristics right there, and they should live right in any of your exponential problems. Okay. And so now that we already knew, we recognize some major characteristics of those problems, right? So let's break it down even a little more here. All right, let's break it down a little more, but now when it gets to this point right here, allow me to start getting to some of the problems, to start bringing up some of the problems right here, and break it down so that I can start showing you that how each of these problems will become an exponential function, or at least how each of these problems can be modeled by an exponential problem. And at this point, I'm starting to use that term model a lot. So what does modeling means? And modeling in mathematics, it means we come up with a function, and then once the function that fits the data given to us. So the 5 problems given there, think about that they are the 5 data from 5 separate problems. Okay, and then we're gonna come up with so according to these data right here, that we're gonna come up with some function that, and now realistically we call those the modeling function, because once we come up with those functions, we can use the function to predict how much that those populations will grow, how in a certain amount of time, okay, or how much that quantity will become, in a future time amount later. Okay, so right now, how about right here in problem number 1 right here, and just now I have corrected the wording here. Earlier I wrote that only 200, but here really it's 2000. So now let's highlight and extract out the information. The population of Utopia was 25 million in 2000 and has been growing by 4.5% each year. All right, so just like what I pointed out right here, there's an initial amount at start, okay, and then it's a changing quantity right here. So this is a little too general, so we can put that aside. We already know that in the problem, it's the population, because it's talked about it's starting out in 2000, okay, and we know that there was an initial amount right there being 25 million there. Okay, and whether or not it's a real country or not, that's not the point. But like I said, if you apply this understanding to some of the actual real the population, the country population, you are more than welcome to do that, if that is some problem that matters to you. Okay, and so the population here is a quantity that's changing. We had an initial amount, and I will get back and extract out that information. Okay, and in the way how it was wording, then that population definitely is growing. Okay, and so the wording is right here. So now the population of Utopia was 25 million. So this highlighted information right here is the initial amount, and has been growing by, see, this year when I'm recording this lecture, we are way past year 2000. So that means that's why it's saying it has been growing. See, this is indicating that the quantity is growing. It's growing by, this is the rate right here, 4.5% each year. All right, 4.5% each year. So now I'm going to leave this information still in the corner of the board right here, but let's recognize from the highlighted information with and align that with those common characteristics that I listed on the other board right there. So the population, so that quantity here is now the population in the problem here. Let's now regard to that as a function p of t, and t here is time. Okay, t here is time in year. And needless to say, any modeling problem is a problem that models how things changes over time. So I didn't even bother putting this as a common characteristic, because it's so common, and it's not only just within these modeling problems we're doing that tentatively to show the existence of exponential function, but outside of the exponential functions, there are other problems that time is a very important variable that's responsible right in each problem like that. Okay, so I didn't even have to mention this, but the variable is a lot of time, or mainly the time is the main variable of the problem like that. So t here is a time, and specifically for this problem is time in year. Okay, so each of those periods of that the rate is measured, we call that, it's we can see that there's an intention that it's time in year. Okay, and so now, so right there, the rates. So now allow me to call that this is the growth. The growth rates. And how I can tell it's a growth rate, because see, it's growing. The wording is saying has been growing by 4% each year. All right, so now evidently it's a growth rate. It's indicating how fast a rate is to indicate how fast a quantity is changing over time. Okay, and so now this rate right here specifically describes a growth process. Okay, and so that's why we call it's a growth rate. And so a growth rate right here is, so for that growth rate, let's call that R equals 4.5, okay, percent per year. 4.5% per year, and time is in year right there. So that means 6 months mean it's a t equals 1/2 because it's half a year. Okay, but then now to be more precisely, this 4.5%, this percent symbol, it really means 4.5 over 100. So more commonly, when we actually use this information into the math problem, I should have said it that way. When we actually use this information in a problem, we have to express this in decimal. So 4.5%, think of that as a 4.5 divided by 100. It's a 0.045. All right, so and so 4.5 of what? Think about it. We're starting out with this information here. We're starting out with 25 millions. So in 1 year later, okay, then we will have 4.5% of the initial population added on top of that, and I will even get to that. But so now I'm trying to explain 4.5% of what? 4.5% of the population in the previous year, of the previous time period. That's what it is. 4.5%. Okay, 4.5% per year, but that means it's 4.5% of the population from the previous year. That's what it means right there. All right, so I'm really trying to break it down in detailed steps. And so now I'm going to update that. 0.45 per year. Okay, and so now outside of this growth rate right here, yes, we're looking at initial amount. All right, the initial amount right here. And I just now realized that my writing was hidden behind that screen, so I'm going to rewrite it at here. Initial amount for this problem is 25 millions. Okay. Okay, so that's the initial amount, and so now just that, and then we have a rate, we know the initial amount. So think about it like this. The problem talks something about in year 2000, and you're still seeing on the screen right there. So year 2000 doesn't mean time. So right in year 2000. This does not mean t equals 2000. Nope, that's not true. Okay, we treat 2000. We treating in this problem. We're treating year 2000 as the initial time. The initial time, that means when we start studying the problem, or in another way of saying, this initial amount happens right at that instant when we reach year 2000. Okay, or when we reach to that year 2000. So that means a t. So the actual meaning of that is year 2000 means t equals 0. Year 2000 means t equals 0. And then the initial amount, that means at that year, right in that year 2000, then there were 25 millions. Okay, there were 25 millions. So now allow me to point out the following. Here's the impact, and this is the only thing I couldn't write it down in the common understanding earlier, but now here's how we can start expressing it. Okay, we call our population as far as a function, and we didn't even come up with the actual function yet, but I know one thing for sure. See, this, according to this information, now we understand that year 2000 means time equals 0. So that means p, our function outputs value, p at 0, or p of t equals 0. equals 25 millions. Okay, this is how I'm indicating the initial amount. Okay, P at 0 right there, or P of 0. Okay, equals 25 millions, and then a lot more, and sometimes quite convenient. P at the population value at time 0. A lot of times, I'm not saying that this is the way of how people are writing it out there, but a lot of times, and many textbook authors is using this symbol, the population amount at initial time, so P sub 0. This is another way of saying that. So P0 equals a P of 0, okay, and then that's the initial amount being 25 millions. All right, so take good note of this right here. This means initial amount. This also means the initial amount. All right, and so that's a few things that I'm breaking it down right here. We're listing that down. And so now I'm going to navigate to the other board. So I've left this here long enough, so now I have to, put that away to get some more work done right here. All right, so now just think about it. Like let's sketch down a quick table over here. This is when t equals, or how about right here in 2000, okay? And this is equivalent to t equals 0. What's the population value? How big is it? How big was the population in year 2000? That was 25 millions. Okay, so now I'm gonna really write it down in actual numbers like that. So in 2000 there were 25 millions people in that country, Utopia. Okay. So now think about, and the wording was describing it has been growing by 4.5% per year. 4.5% per year. I had that information written down right here, 4.5% per year. Okay, and so that means in 2001. Per year, that means in every 1 year away. So now that means t equals 1. When t equals 1 year later after this, after the initial amount that we start looking at, that we start studying the problem, after that initial amount, 1 year later, this is what will become. You see 4.5% of, when it say, and I explained this earlier, 4.5% here means 4.5% of the preceding year. So if you would like to find how big that population at this time instance here, 1 year later, we have to think about 25 millions, but multiply that with 0.045, because this is 4.5%. That's just to indicate how much added to the initial. So the initial is here. But we add 4.5% of the beginning of the population in the previous time period. 4.5% of that added on top. That's how it happens. Okay, and so now that means here in the way how I'm seeing, all of a sudden I realize that mathematically 25 millions here, but add with 25 millions times 0.045. So that means we have a common factor here. So anyone learning in calculus should be familiar enough with the algebra, at least with the common factor thing. We can surely factor out, and I didn't even have to pull out any calculator yet. 25 millions. After factoring it out, we're looking at 1 plus 0.045. 1 plus 0.045. Okay, because this is 25 millions times 0.045 here, and then this means 1 times 25 millions. So factoring out that common factor, we're looking at this quantity. But let's make it even simpler for our lives right here. 1 plus 0.045 is exactly the same. Now allow me to just erase that and change that to the updated value, 1.045. So that means 1 year later, after the initial year, 1 year later, we're going to our population is going to become this much. 25 million times 1.045. So now I can even allow me to even erase this because I need space for the later steps of the table. And I'm going to just write down this finalized value right here. And I purposely leave the calculation out. I only write down the thought process, 1.045. That's what happens in year 1. I mean year 2001. A year later, that's when t equals 1. And so now with that amount, allow the work to grow a little bigger here. So now, like I said, I decided to leave the calculation out, but anyone anyone is welcome to use your own calculator and punch it in and get an actual value for this. But it's not important. It's not really important. As a matter of fact, doing that will take away some good usefulness of this. So I want to leave it like this for now. But keep in mind the whole expression here, whatever real actual value coming out from this, that's the population, how big that population in 2001. That means 1 year later, t equals 1. Or in other words, this is the same as p, population of 1. This is, we already know it, this is p of 0. All right, let's go further. So now in 2002, this means t equals 2 years. 2 years now counted from year 2000. That means, there's 2 years gone by. There has been 2 years gone by. Okay? But now remember, the rule of this growth here, the rule of this growth here is that we only know, according to the data, we only know that the population grows by 4.5% per year. That means if we're looking at the 4.5%, that means this year it will grow by 4.5% from the last year, not from the very first year that we're looking at it, not from the initial year. So now does t equals 2, or in year 2002 right here. Okay, then we're going to go, we have done the math there earlier, so 25 millions. Okay, times 1.045. This was the amount from the preceding year. I'm going to grow that. It's going to grow by 4.5%, which is in decimal 0.045 again. That's how it happens. But then that's just how much growth, how much grown after that previous year. But now to find the total amount that we still need to add this to that amount from the previous year. That's the idea. And so I need more space here to write. So now that's 25,000 times 1.045. Okay, but we're adding that. But hey, wait a minute. There's both of these terms right here, with the addition right in between them, both of these terms have the common factor that I underlined right there. And so now, in other words, I can rewrite this as similar to what I've done earlier. I'm going to factor out this common factor, and I'm still leaving that in the the version where without calculated, without the calculation. And so 25 millions times 1.045. This is our common factor. Now I'm going to open another parentheses. What's in parentheses really is a 1 plus 0.045 again. It's another 1 plus 0.045. So that means what it tells me here is that altogether this is a factor of 1.045. This is another factor of 1.045 because it's 1 plus 0.045 is a 1.0445. All right, so that means putting it together, now I can come up with the following and allow me to again erase this here to make some space for myself. But in year 2 right here, I'm looking at 25 millions multiplied with 1.045, but really it's square. So 2 years gone. So we already had the factor here after step 1. And now in step 2 that we multiply with that same factor there, but now in square. Okay, that's now being squared. All right, let's even try to recognize further. So 2 years gone by, and this value right here is, we can understand that as the population when t equals 3, p of 3, p of 3. All right. And so now in 2003, this is when t equals 3, 3 years later, after that initial time like that. So now again, anyone watching the video up to this point has been fluent enough, and it's time for me to start picking up pace here, but 25 millions times 1.045 square from the preceding year. We need to add with 0.045, or we need to add with 4.5% of this. Okay, so now meaning we're looking at 25 millions, okay, the current value, multiply with 1.045, but already square. I'm going to multiply with another 0.045. That's how things happen. It's a square here, okay, and then there's multiply with an extra 0.045, not 1.045, an extra 0.045. And then now again, I'm recognizing there's common factor, right? We can factor it out, and for anyone watching this, you are in a pre-calculus course, so you should be decent enough with recognizing these common factor. So that means in my next step, I can factor out the 25 millions times 1.045 square. That's the common factor. But now what's left behind in the parentheses is it's 1 plus 0.045. So another 1 plus 0.045, which gives us a 1.045 again. All right, so now it's another 1.045. After we're adding one with the 0.045. So that means altogether this allow me now to erase the one more step right here. So 25 millions, okay, times 1.045 cubed. All right, cubed. And this is when, and I have to correct this, but earlier I had a typo here. It was 2 there, and now it's 3 here. Okay, so I believe I've gone far enough, and anyone following along with the video here should be able to recognize this. Okay, because according to this way right here, see, so now make a very good prediction right here. What about in year 2000 T? Allow me to write things a little awkward that way, but I mean in some t years after 2000. So now when t equals 0, it's that initial amount, p of 0 equals 25 millions. 2001, this is t equals 1, okay? And we've gone that much. So it looks like I can use the following term right here. You see this factor right here. All right. So it's not the growth rate. It came out, it's derived, it was derived after the growth rate. But this here is called growth. It's a growth factor. All right, it's a growth factor. Okay, so any one of this has a growth factor. So for this problem, 0.045, our problem number 1 right there, 0.045 is regarded as the growth factor. It's indicating how fast the growing process will be. All right. But now back to what I was saying earlier. In year 2000 OT, I mean in 2010, that means t equals 10. 2022, that means when t equals 22, so 2000 OT, okay? Or in t years later. In t years later. In t years later. All right, so ladies and gentlemen, whoever is watching this with me right here, you should now have a great way to theoretically predict how big the population of utopia is in year 2000 t right here. 2000 t. That will be the population at some t time, and that equals, see, the repetitive pattern here so far has been 25 millions. That was the initial amount. That was the amount at start. We're going to have, it's going to be 1.045 as the growth factor, but we raise that to the power t. P of t equals 25 millions times 1.045 to the t. Now I'll put it in a box. And I did not formally bring up any question. I just sketched down a problem and pretend that any one of us watching this video is a researcher doing this kind of work right here. We don't really have any definite question for ourselves, but we just keep exploring, brainstorming ideas in different directions right here. But at least now in this pattern that I'm seeing, that they're predictedly, okay, as a way to predict, in some t years later, generally in some t years later, there has to be this growth factor that now I formally give it a name. This growth factor right here is 1.05 raised to the t, the exponents t right here, and multiply that with a constant coefficient, 25 millions. All right, so now ask yourself this question. This function looks, this kind of function, or this function itself looks like some kind of function we have seen before this. And yes, ladies and gentlemen, this is an exponential function. It's an exponential function. It's an exponential function. Okay? So here, for this particular problem, we're looking at, and problem 1 right here, we're looking at the population at any time t equals 25 millions times 1.045 to the t. So now clearly we realized it is an exponential function in the form of an f of t, in the form of an f of t equals to a constant coefficient times a to the t right there. And so now if we refer back to that lecture where I was giving the teaching about an exponential function, this was one member in the whole general form, in the whole family of all general exponential function. All right, that's the one. All right, so now we've just now finished pointing out how exponential functions exist out there, and it lives right in our problem. But so now, for the later problem, I will also work through the process, okay? And these are not examples; these are just problems where I start pointing out, where I can point out how how exponential functions exist out there, okay? But then for the later problems, as I get into it, I'm going to pick up the pace a little faster because this first one right here, I have to really aside along the way explain a lot of explanations, give in a lot of explanations. But now once you got in gear with that understanding, then we can start picking up the pace right here. All right. Now for problem number 2 over here. Okay, let's quickly read the wording of the problem right here. And again, this problem comes with no question. It's just the description of, think of this as the data that we're having right here. So the population of a certain bacteria started with 11,000 of them initially and doubles each hour. All right, the population of a certain bacteria started, so we can call this population another function that changes over time right here. So P of t is right here. All right, and so now we can refer to our population of bacteria. Okay, so the quantity or the population here, we can refer to that population as a function P of t again. It's a population P of t is a function that time is the variable that's changing it. All right, and so yes, time here, and so according to this problem right here, the wording is making it clear the population of a certain bacteria started out with 11,000 of them initially and doubles each hour. So we want to tackle down right here to this, and so my keyword right here, the keyword I recognized here, it shouldn't be even my, it wasn't even my keyword, it's just the keyword we recognized here is each hour. So that means time is, at least time is the variable that's measured in, t is the variable that's being time measured in hours. Okay, so t equals 5 means 5 in 5 hours, t equals 10 means 10 hours, t equals 2.5 means 2.5 hours. All right, so t is a time variable right there. And so now, just like what we've done earlier, the bacteria is growing. So how do I know it's growing? Because it doubles each hour. Okay, this amount of bacteria. So now allow me to tackle in right here with the initial amount first. Okay, so there were at start we had 11,000 of them initially. So now I'm going to refer to this as the initial amount. So now as far as initial amount, all right, I am looking at 11,000. Okay, I'm looking at 11,000. And so in the way how I explained, just like how I explained that in problem 1 earlier, start nailing this down. This is time. This initial amount means time equals 0 at that, when it was that amount particularly. So that it also means in the concept of this function, it also means t of 0 equals 11,000. P of 0 equals 11,000. Or another way of saying, another symbol, another notation, P sub 0 over here. Very commonly used among the mathematicians or scientists who work with these exponential function applications. Okay, and so of course, we've already seen one problem, how we derived a function, a modeling function that goes exponentially. And I didn't say we have finished looking through, but at least I already pointed out that right there through problem 1 there was an exponential rule that we have seen. And so and I stopped right there, and then we moved on to example 2. To problem 2 right here. Okay, so right now P sub 0 equals to this. And so it's growing. So let's find out the growth rate right here. Okay, the growth rate here is a little tricky to find right here because the term is indicating, according to the term, it's indicating it doubles each hour. Double each hour. Okay, it double each hour. All right, and so it's not written in a form of like a increase by 5% each hour or increase by 20% each hour. It was not written that way, but the growth rate here, this is only the clue right here. It's doubled, right? Each hour. Okay, double each hour. So now to clearly understand, it means so doubled each hour means 100% is added to the population of the previous period. It was added to the 100%. Okay, it's added to the period, to the population of the previous. So of course 100% of the population. Okay, from the previous period as well, and is added to that. That's why I use that in the short form right here. That's how we get double. Okay, and so now with all of this understanding, let's get to the other board and try to derive the work right here. Okay. All right, so now very similar to problem number 1 right there. So initial amount, or when t equals 0. Now the table can get a little more organized right here. When it's t equals 0, yes, we start out, this is initial time, we knew that we got 11,000. And yes, this is clearly p of 0, the population at initial time. Okay, and then now 1 hour later, t is measured in hour. Okay, so 1 hour later, t equals 1. And this is where it says clearly right here. So in how I was explaining from the previous problem, then initial amount at start, I'm going to add to 100% of that initial amount, because only 1 hour later, and I explained double means it's 100% is added to the preceding step, to the preceding period. Okay, so that means in the preceding period, right here when t equals 1, the preceding period has to be just the initial time. Okay, and so the initial amount I'm going to add to 100% of that, and 100% is simply just one time. Okay, so 11,000 added to that, and that's why we ended up with double. But now I prefer to write it as 11,000, because factor out that 11,000, we're looking at 1 plus 1. See, so this one right here is, after we putting out the two ones right here, after putting out the common factor, we have 1 plus 1, but this one right here is simply just a factor, but this other one right here, think of that as 100%. Okay, this is as 100% right there. That's what this one is all about. Okay, but now a little further, I see that this is just 11,000 multiplied with 2, and allow me to leave the calculation now. I'm leaving that here as 11,000 times 2 for a reason. Okay, and this is how I'm seeing it. And so that factor now appears to be consistent with the description. It doubles each hour. It doubles each hour. Okay, and so now let's look at step 3. I mean, this is step 1 right here, so let's look at step 2. When t equals 2, this is now our population amount from the preceding step, from the preceding period, from the previous period. So 11,000 times 2. I'm going to add 100%. I'm going to add 100% of that to that. Okay, and so that means 100% of this current amount, 11,000 times 2, added to that. Common factor. I can factor this out as 11,000 times 2, but in parentheses 1 plus 1. Okay, and so this is the rate right here. But now I see 1 plus 1 is just simply 2, and so 11,000 times 2 squared. Start observing the pattern again, the repetitive pattern. So now it doubles every hour. So when t equals 2, we're looking at 2 squared, 11,000 times 2 squared. Let's proceed in one more step right here. So when t equals 3, all right, so we should be looking at 11,000 times 2 square plus 100% of that, 11,000, because see, when t equals 3, it's 1 hour later after t equals 2. And so we're just simply going to add another 100% of that much from t equals 2. So now 11,000 times 2 square, 100% of that. And now I'm going to clear this away. All right. And so now that gives me, after factoring out this common factor, it's 11,000 times 2 squared, but I have in another set of parentheses 1 plus 1. This is another 1 plus the rate. And that is famously the growth rate, 100%, growth rate 100%. Okay, and so now that means we're looking at, for this particular problem, this step right here, when t equals 3, we're looking at 11,000 times 2 to the third power. All right, and so now again we see enough repetitive pattern to see, hey, so think about, wait a minute, if we are at time t, okay, so now generally if we're at some time t, some t hours later, okay, I should have said at t hours later, and I mean after the initial time like that. Then now needless to say, and so this was, I should have also mentioned, yes, this amount is p of 1, see, power 1, okay, and this amount here is p of 2, right here, the population function of 2. We didn't know what that rule for what the rule of that function is yet, and we're working on our way. We're on our way to find the actual rule that runs behind the scene here. Okay, so p2, it turns out it looks like it's 11,000 times 2 to the square, so 2 here is consistent with that 2. Okay, and then now it's 11,000 times 2 cubed right here, but this is the same as the function value when t equals 3. So p3, p of 3 equals 11,000 times the 2 cubed right there. So now this is how we can make that conjecture, okay, that generalization. Hey, so it should be that at t hours later, at some t hours later, then the population at some t hours, p of t, has to equal, see, so now I'm what I recognize here. P of t equals 11,000 times 2, but so now 2 to the t here. All right, 11,000 times 2 to the t. All right, and so now once again I'm going to break down a few more things before I swing back to the other board. So in this way, in the way how I'm explaining, we see the exact same the exact same common characteristics from the earlier problem that I broke it down right there. So this is our growth rate right here. So this number, okay, this is the growth rate. But now after adding the growth rate with 1, and we saw this in the earlier problem as well. This is some other generalization that I could not point it out when I was pinpointing down the general characteristics, okay, the common characteristics. But now as we work through the process, we can see it's so far it's been two problems. It's been the growth rate added with 1, the growth rate added with 1, okay. All right, so that's the growth rate. But then after adding the growth rate with 1, we come up with this is called the growth factor. Okay, so in the same language we picked up from the earlier problem, this 2 right here is the growth factor. So it looks like we can now become a little more flexible. When the wording of the problem, instead of indicating directly, sometimes the wording of the problem, instead of giving directly the growth rate, so growth rate here is 100%, okay, that's how it's associated. But so now be aware that sometimes the wording can be, instead of telling you directly the growth rate right here, the wording of the problem can be simply just telling you that this is the growth factor. Okay, growth factor. All right, and so it's so now flexibly speaking, later on when we have any problem where instead of giving a direct growth rate, but you are given just a growth factor, then that growth factor is also going to just your form in a function. So now from the earlier board, I've recognized that our final function was p of t. Okay, p of t here came out or concluded to be 11,000, okay, times 2 to the t. We concluded this 11,000 times 2 to the t, where this 2 to the t shockingly turned out to be simply just that growth factor that was given. So now again, back to what I was saying earlier, a lot of times the problem, instead of giving you the growth rate, it just simply gives you the growth factor already that maybe we didn't realize it. But now I put in different wording so that you can start realizing how it works for us. But now wait a minute, this function again, after we've come up with that, and so the function that we come up in in problem 1, and now the function we come up in problem 2, these are all functions that serve in the same purpose. From once we arrive at the function, we can use this function to predict. I can use this function here to predict how many bacteria in my population in 10 hours later, in 2 days later, and 2 days is equivalent to 48 hours. Okay, so in 2 days it means I can calculate P of 48 by simply going through this rule over here. And that's the whole usefulness of coming up with any modeling function, because once we have finalized a function, okay, a modeling function, and we can use that function to make prediction about how big our population will grow into, how big our quantity will grow into. All right, so that's for problem number 2 right here. And now let's look at problem number 3. All right, so for problem number 3 right here, the process is even going to pick up faster compared to the process that we've had earlier. So $4,000 is invested in a bank account at an interest rate of 7% per year, okay? Or sometimes you may hear people say 7% annually, okay? So 7% per year, and we have 4,000 being invested. So now this problem right here, we are looking at calculating the amount of money, right, that will grow into in our bank account right here. So back on my board, I've been using the word population, okay, but that's for the problems that more scientific problems. But here, when it comes to financial problem, then we don't use the term population. Technically, it's a population of money. All right, but here we call it just the amount of money, right? The amount of money, or just the quantity. Okay, so now I'll just call that the quantity. All right, and so that quantity right here, now we can call it as Q of t, the quantity. And will it be an exponential function? Because we've explored 2 problems already, and they both came to exponential functions. Okay, they both came to exponential functions. So let's look at this problem number 3 right here. Will it be an exponential function? All right. So what's given to us? So now with this problem, I highlighted it earlier, and now let me bring it on just in one corner of the board right here. But that 4,000 that you are seeing right there, okay, that is the initial amount. Okay, the initial amount, or the initial amount be 4,000. Okay, and this is the same as Q at equals with Q of 0 right here. Okay, it equals to Q of 0. This is because this is when t equals 0. Okay, and so how do I know that this is how do I know that 4,000 is the initial amount right here? Because think about it, when you start doing your investments right here, somebody does an investment earlier than somebody else. So the time that you bring your own money into the bank and hand it over to the bank so that the bank can start borrowing from that moment on, that's when it's called time 0 right there. Okay. So not because you're doing the investment starting in 2009, and that means your t equals 2009. Nope, right at that instant that you lend your money to the bank, that you lend your money to the bank, that's where your money is going to start growing. Your amount is going to start growing. So I explained this earlier. Now I'm going to really tear it in depth right here. But think about, if we're still looking at the whole description of the problem right here, we have money. Ideally, maybe unused money at the moment, so we want to make some good use out of it. Hey, the bank needs money. Okay, we bring it to the bank. The bank technically is gonna A saving account to us means we're going to let the bank borrow our money right here. Okay, and as they borrow our money to do their business work there, whatever work right there, and then they're going to reward us for lending them the money. Or basically it's a way that they're paying us. That's what interest rate is for. That's what paying interest is for. Okay, so the bank in this position, in this problem, we are in the position of the lender, and the bank is indeed the borrower. But it's just sadly we don't have the control over, you know, to decide how much interest rate we charge them. But they already offer an interest rate. They offer to us. So what matters is whether we agree to invest with them. That's all. But basically the idea is we are the lender, and if we give the money to the bank and the bank pays us the interest, that means we're making earning out of our money that we're not currently using. That's the idea right there. And so that's why the bank sets a rule that, hey, we're only going to pay you the 7% with this amount you're bringing in right here. Our bank has a policy that we're only going to pay you 7% annually. That means each year your money is going to grow by it's going to grow by about 7% of what you brought in today. I mean, next year, just precisely next year, your bank is going to, your money is going to grow by 7% of whatever you brought in today. And then in the year after that, it's going to grow another 7% of what's happening at the end of next year. That's the idea right there. But so interest is what the bank is paying us for lending them the money. Okay? And then we, in financial term, we call it the interest. And so indicating how fast it goes, it's called the interest rate. It's called the interest rate right there. Okay? And we will get into the even more, and if anyone watching this video happen to, you know, to be later heading out for the business math, your professors there at econ and business courses will, you know, focus even more into these. So that means now extracting from the information I was explaining here, then that means we have a growth rate. I try to use that common term throughout all problems. So the growth rate in this particular problem here is the interest rate. Okay, it's just the interest rate. Yes, financial has different language sometimes. And so now it's given that. So we know that our money will grow by, so this time right here, it's really the rate right here, it's 7%. Okay, per year. That's how we know it. All right, so we know an initial amount. We know an initial amount. We call our quantity that's changing over time a Q of t right here. And yes, I forgot to mention it, but now it's needless to say right here. This is, so the time here, t is going to be time. T here is going to be time in years. Time in years. And so this 7% is written as 0.07. Okay, 0.07. All right, but now with just that much information, we have enough with this much given information right here. We just have enough to get the calculation done right here and come up with our function. All right, so just like that, when we start bringing in the money in the bank like that, then we are at time 0, or the initial time, t equals 0. So that, needless to argue about that, we're looking at 4,000 being our initial amount. Okay, being the initial amount right here, 4,000. And so it's just for anyone who will have some intention, or anyone watching this already has some intention to go into the business math right here, or financial math. Initial amount is also in financial math is also referred as the principal value. Okay, principal value or present value. That's the same concept for that. Okay, and so, but now let me put that away. this, mathematically speaking, is the function value, or this is q of 0. Okay, or yes, I've introduced this symbol earlier, now I can use it again, q sub 0. All right, and so now when 1 year later, time, remember time is measured in year. Okay, so 1 year later, we're looking at 7%. So 4,000, but add with 7% of 4,000. So 4,000 times 0.07, that is 7%. And so doing this, I can again see, so it's very similar with problem 2 and similar with problem 1, that general structure is here. So I'm now looking at with this, factoring out the 4,000 as a common factor, I'm looking at 4,000 times 1 plus 0.07. And so just that same common generality with the earlier 2 problems I brought up as well. Rates, growth rates, or now specifically in financial math, interest rate. Interest rate plus 1. Growth rate plus 1. We saw this in the earlier problem. Okay? So to underline this, this is the growth rate. Okay, that's the growth rate right there. Okay, but then really that means our function there can be rewritten as that. I mean that calculation there can be rewritten as. Okay, so I need a little bit more space here. That calculation can be written as 4,000 times 1.07. All right, so this final form right here is the same as, this is quantity, amount at 1 year later. 4,000 times 1.07. And once again, in the same terminology that I have brought up earlier, this is not the growth rate, but this is called the growth. This is called the growth factor. All right. So now let's continue with our work right here, because we don't want to only just invest for 1 year. I mean, if anyone, I doubt if in reality any bank would offer just a short-term the investment like that that only lasts for 1 year. But you can always ask. Who knows? Okay. And I'm talking about. I'm not talking to any of my students who does have some plan or some intention to go head out there and start doing some investments like that. And so when t equals 2 years later, let's see what can happen. 4,000, but so now from the previous year, we had 4,000 times 1.07. Okay, and I'm going to add with another. I'm going to add to another. Didn't have enough space here, so 4,000 times 1.07. I'm going to add to another 4,000 times 1.07, but times with 7% of that. It's just, this comes straight out from the rule of paying interest. So the whole idea from problem 1 to now is that that's interest, or that growth rate accumulates from every step from the beginning. And that's how it happens here with our banking right here. So it keeps accumulating up, okay, from the initial time, it keeps accumulating up. And that's why I break it down in a problem like this. And so now, again, common factor here is 4,000 times 1.07. So now I can rewrite all this here. So I've done this repetitively enough, so I'm going to just skip straight to that. So eventually it's going to break down as 4,000 times 1.07, but square them. Okay, because in the way how I'm seeing this, then this is 4,000 times 1.07 in parentheses 1 plus another 0.07 right here, because we have, see, this is the factor over here, so we have a 1 plus 1 time plus 0.07 right here. 0.07. Okay, that's because this is 1 time, this is 0.07 time of that. All right, but now there's no need to write that. And that is the reason why I have another 1.07 factor. So this is growth factor again, being square. And so this now gives me, this is my Q of 2. That's what it is. All right. And so now in my next step right here, when t equals 3. Okay. And now I can, again, repeat the process right here. So from the quantity of, after 2 years, from the quantity at the end of 2 years right here, 4,000 times 1.07 square. This is the amount that expectedly to get at after 2 years right here. So I'm going to add with another 7% of that. So 4,000 times 1.07 times square times 0.07. Okay. And so that is 4,000 times 1.07 square times 1 plus 0.07. Okay, and that gives me 4,000 times 1.07 cubed. 4,000 times 1.07 cubed. All right, and so now this is the same as Q3 right here. This is the quantity when it's t equals 3. So now we can start thinking about the long term in the long run right here. When, okay, so at t years or in t years later. Okay, in t years. So when it's 3 years, it's Q of 3 equals 4,000 times 1.07 to the third power. In 2 years, t equals 2. Q2, Q of 2 equals 4,000 times 1.07 square right there. Okay, so now we can generally predict that in t years, we're looking at Q of t generally should equal 4,000 times 1.07 to the t right here. And that's how it is. That's how it is. And so now that means we have come to we recognize now that this quantity function is modeled by 4,000 times 1.07 to the t. But what I want anyone viewing this lesson is to recognize it's again another exponential function. Okay, so we come up with this. It has always been 1 plus with the growth rate. Okay, 1 plus the growth rate here, but the whole thing is called the growth factor. Okay, and then so in the end, our function forms into that the initial amount right here times the growth factor to the t power. The initial amount is here, and we have seen that also in example 1. I mean in problem 1 and problem 2 that I didn't have a chance to mention, but now after doing 3 problems, we can start mentioning it. Okay, and so these are the problems where our quantity is growing. All right. All right, and now here we are at problem number 4 over here. So before I get into problem number 4, I just want to have a word that we don't necessarily have, in this particular discussion right here, I don't necessarily have to advance into problem number 5 later, because problem number 4 already has a lot of the generalizations that also included in problem number 5. And so once we've learned through how we can find a function that models the changing process of this problem 4 over here, then the problem number 5 is going to be done very similarly. Okay, so for problem number 4 over here, let's have a look at the wording description right here. And again, this problem is just like any other problem. It did not come with a question. So all it brings up here is some data that was observed. So 10 milligrams of bismuth 210 isotope reduces about 13% each day. 10 milligrams bismuth 210 isotope. So bismuth 210 bismuth itself is a chemical element out there, and bismuth 210 is known as an isotope. But precisely what it is, it takes a formal course in chemistry to understand, to have a complete full understanding of these elements and as well as their isotopes. But now, so right now, briefly for anyone to understand, or generally enough, then it's just a chemical the element. And then the wording that caught my attention here, that should have caught any of your attentions as well, is that it reduces. So we're starting out with some amount, some quantity, and then it reduces. All right. So the reason I brought this up, the reason I brought up this problem is that in the earlier problem 1, 2, 3 that we have done earlier, it was all about we gaining more. The quantity was changing, but in the end we got more quantity over time. But this problem start bringing any one of us into it's a similar process. It's a process where the quantity itself is changing. It's just the nature again. Okay, it's just the nature. The quantity is changing, but in this case, in this problem right here, it's changing in the way that it's losing itself right here. See the wording right here is indicating that. So expectedly in many days later, after we set out with 10 milligrams of bismuth 210 right here, then some days later we're gonna expect to lose some mass right here. We're gonna lose some amount of bismuth 210. It won't stay the same being 10 milligrams any longer, and that's the whole idea over here. All right, and so in this way, let's go ahead and form into some. Let's set up some formulation. Okay, let's do some similar formulation as how we've done in the earlier problems. Okay, so as far as I recognize here, we have a quantity. So in this particular problem, if that we're interested in, then the quantity that we're looking at, the quantity that we are monitoring, the quantity that we're modeling is let's call that some Q of T. Okay, we have a quantity and it's the amount of bismuth right there. Okay, and so right from the wording, then we already see that initial amount is given to be 10 milligrams, and milligrams is a very common unit for chemists to work with right there. That's in the small scale amount like that. So 10 milligrams. So this is the initial amount. Okay, because we're starting out with that. The wording is making it clear that 10 milligrams of bismuth 210 isotope reduces about 13% each day. So it may not even specifically indicate that this is the starting, but once we're reading a question like this, we understand clearly that we understand that it has to be a starting amount, and then from there on, whatever time that is, whatever the day that is, or whatever instance that is. But after that instance, 1 day later, we're gonna lose 13% of that initial amount. 2 days later, then we're gonna lose another additional 13% of the amount right there. Okay, so. And that's the idea. So when I was still having the wording description, then we also noticed there's a rate, right? But this time, see, we don't the quantity itself doesn't grow over, throughout the days right there. But instead, the quantity is losing itself. Okay, so this is a phenomena. Okay, this is a phenomenon where we call it's a decay process right there. Okay, so in the earlier problems where population was growing, or the bacteria was growing, or even money was growing, it was a growth. And here in this problem, the quantity is losing itself. So opposite from being a growth, this problem introduces us to a process where the quantity is decaying itself. It's losing its own. And so formally, as a term, we call it's a decay process. Okay. So now allow me to use this term right here, and this is the first time for somebody, this may be the first time hearing that term right there. It's a decay. So now we saw a rate earlier given in the problem is a decay rate, and the decay rate given in the problem was to be, so it's 13% each day. All right. The wording was indicating that it's about 13% each day right there, and that's how I understood that we had a decay rate right there, and see the formal, I mean the beginning term I use here, the daily term that we're using here is reduces itself. This starting amount is reducing itself right here, but reducing in formal term is a decay process right there. And so now once things are breaking down, things are decaying, right? And we have here in this problem that 13% is the decay rate. Okay, so it's decaying about this amount of bismuth right here is decaying at 13% of itself each day. And so we will get more into that. And so it just means, so if the term is being too formal for anyone, just think of that as the amount is losing itself, taking away. Okay, it's losing itself 13% of the previous one, okay, on each day. All right, and then I will get even more into that when we sketch down the actual work. All right, so we got the rates. So it's still similar. Once I list down these things, you can still see that it still carries all of the major characteristics. The quantity at any time is here, okay, and the quantity and that we want to study that's changing. And then we always have an initial amount. And I also could have also mentioned this initial amount right here is the same as if we call our quantity with the notation Q of t, then this is Q at time 0. This is when t equals 0, okay? Or as a notation, Q sub 0 over here. A lot of people is calling it that way, okay? Because this is when we're starting out, t equals 0. Okay, so t equals 0 is down here. All right, and so now, and yes, aside from that, t is going to be the time, okay, in days right here. That's measured in days this time. So every problem has a time variable. Problem 1, problem 2, problem 3, and now problem 4. Every one of the problems we've done had a time variable, which is the time t, but it's measured differently. So some problem we're looking at per day, like right here, this problem right here, the time is in days. Some other problem, times is in years. Okay, and in some other problems, time could be in hours, or so the bacteria problem was time the variable for time was in terms of hours. Okay, so time could be but the idea now is that time is broken down into a subunit. Okay, so these are units of time right here. So days or months or weeks, okay, or the hours or seconds, minutes, years. All right. So that we have a time variable. Okay, so now let's advance to the other board right there and sketch down the problem. All right, so on this board right here, here's how I'm seeing it. Just very similar to the earlier work. Of course, it's different a little bit. It's slightly modified, but very similar. I'm going to start out with when time is at t equals 0. That's right at the initial time. Okay, the initial time. I may have not used this term yet. I might have not used this term yet in the earlier problem, but when t equals 0, we call it's the initial time. Okay, and so when time equals 0, here's what happened. Our quantity stays right at see, that's why I call it Q of 0 formally, and then this is exactly 10 milligrams. All right, and so we can also notate this as the Q sub 0 quantity. So as far as a general notation, either we call it Q of 0, because indicating that if it's a function, then it's the function at time equals 0. Okay, but then together that symbol here we can use a shorter symbol, Q sub 0. But then the actual quantity here is 10 milligrams at start. All right. So now we can start utilizing the decay rates into the problem right here. So decay means it's losing itself. So the rate was indicating that the problem, I mean the amount is losing itself 13% of itself each day. The quantity is losing 13% of itself each day. All right, and so in that way, when t equals 1, that means 1 day after the initial time. 1 day, exactly 1 day after the initial time, and this is what we observed. And so the rate is what observed. It's always been like that. The rate is whatever being is a rate that's observed. Okay, at least for those scientific problems that we've done earlier, aside from the money problem, aside from the financial math, then you can start also further seeing that the rate is observed. It's just nature. All we can do at our best is observe the nature, and then we may recognize a proportion, or we may not recognize the proportion. But any of these rates right here came out as an observation. Okay, so t equals 1. 1 day after initial time, so in what we have observed, 13% is lost. 13% is lost. So here's how I'm seeing it. Starting out with 10 grams, so that's for day 0. That's for 0 time. I shouldn't even say day 0 right there. That's for 0 time. But exactly 1 day later, we're gonna only have 10 minus 10 times 0.13, because 13% is lost. 13% is lost means we're going to take away 0.13 of that initial amount right there and take that away from the beginning. So the beginning amount is here. 0.13 or 13% of that initial amount is 10 times 0.13. Okay, so these are basic math that hopefully I don't have to spend too much time explaining, but taking that away. So I don't really intend to get into a final calculation, but the point now is that there's a common factor, okay? And so it comes out 10 times 1 minus 0.13. 1 minus 0.13. And 1 minus 0.13 is indeed the same as 10 times so 1 minus 0.13 in decimal or mathematically it comes out being 0.87. All right, so that means, just think about it, as somebody can think of that as taking away 0.13%, or somebody can think about this process as, 1 day after the initial time, then the amount only becomes 87% left. That's another way of thinking. We took away some loss. We took away some quantity, so we have lost some. We've lost 13%. But that means this is how much remains right here 1 day later. So we have about 80% of that material remains. All right. And so there's still a factor similar to the growth factor. There's still a factor that's similar to the growth factor. Okay? So if this was a growth process, then think about after 1 day it has growth. It has grown into some proportion of that. Okay, some factor of that. That's why it's called growth factor. But here we had things. We had the material breaking down like that. So this is now instead we call that it's a decay. It's a decay factor. All right. So yes, right here, this 0.87 right here, we can call that the decay factor. Okay. All right, the decay factor. So that's what's happening at the end of day 1, or basically that's what's happening exactly 1 day after initial time. Like that. And yes, again, this is the decay right here. This is the decay rate. All right, so I'm making it clear in that. So decay rate and decay factor is slightly different like that. But so now, unlike what we have seen earlier, so when it was a growth, then we add with the growth rate, okay, to get to the growth factor. But now in this problem, the problem becomes a decay problem where material is losing on its own right here. Then we're gonna go with 1, but subtract. I'm gonna start putting in. This is where I start noticing some difference with the problems we've done earlier. Okay, and then so we subtract the decay rates from 1, and then that's how we end up with the decay factor. All right, but now we are ready to advance to the next step. So now for 2 days after the initial time. So 2 days after the initial time, but that means another 1 day after t equals 1. Okay, but so that means we go from whatever is currently. We go from whatever is currently the amount. So this is the, so when it advanced to T2, right, T equals 2, then the current amount now is 10 times 0.87. And I didn't even bother getting a calculated value for that, because that's not what my point is. Okay, so 10 times 0.87, the current amount. Okay, the current amount, or at least the amount in the preceding periods, in the previous periods. From that amount, I'm going to take away the lost, because see, this is the amount currently that remains at the previous period. But now I'm going to take away another. I'm going to take away another 0.13 of that amount. See, so it's always we multiply the current amount or the amount from the previous periods multiply with the decay rate or just the changing rate. Okay, and then here it's a decay process, so we're going to subtract it away. We take away that amount. But see, again, common factor. And so now I can factor out the 10 times 0.87, and then have left behind 1 minus 0.13. And so now doing that, it will give me, in one more step, 10 times 0.87. But see, wait a minute, 1 minus 0.13 is another 0.87. So 0.87 times another 0.87 right here. See, notice this is another 0.87. So that's why now in the final expression here, I'm looking at 10 times 0.87 squared. So there you go. This is that decay factor again, and this is that same decay rate. Okay. So when t equals 2, or at the end of 2 days, right there, at exactly 2 days, after the initial time, we have about 10 times 0.87 squared that remains. All right. So now let's look at the next one. So for the next one, when t equals 3, okay, when t equals 3. So the amount from the previous period, because now we're for another period, we're in the third period, so the amount at the end of the second period, okay, 10 times 0.87 squared. That amount from the previous period, we're going to have to take away another 13%. So things keep accumulating. In those growth processes we've seen earlier in problems 1 through 3 earlier. The growth accumulates from the previous periods, and here the decay process also accumulates from the previous, the very immediate previous period. Okay, so now that means 10 times 0.87 squared. I'm going to subtract 10 times 0.87 squared, but multiply with a 0.13 of that, because that's how we're indicating we're losing 13% each day. So for that third period, for when t equals 3, we lose another 13%, but on top of whatever came out from second period. That's the idea right there. Okay, and so now mathematically speaking, again, common factor, see, common factor. So now I'm looking at 10 times 0.87 squared, but multiply with 1 minus 0.13. And again, wait a minute, this is 1 minus 0.13, another 0.87 is found right here. So that means 10 times 0.87 squared times another 0.87. So that means exactly 3 days after the initial times, then we have only whatever comes out from 10 times 0.87 cubed that remains. Okay, whatever comes out from 10 times 0.87 cubed, that's the amount that remains after exactly 3 days after the initial time that we started out with 10 milligrams. And that's the idea right there. All right, so from this way how I'm seeing it, from this way how I'm observing it, okay, now my board here is getting tight, so allow me to get to the other board right there. All right, so now we are ready for some formal, for some generalization here, some formulation. So just think about after or in t days, okay? So in t days, Because now see, and the wording in this time is right here in the description is right here on the board. Here, time is a variable. T is a time variable that's measured in days. So in t days right here, the quantity is expected as Q of t. Okay, and I can also swing back to the other board and make some extra notes right here. But this quantity, if we're making a good observation, 10 times 0.87 to the first power, this quantity here is referred as the quantity in 1 day. This is Q1. That's the amount. Okay, and then for day 2, I mean for t equals 2, or 2 days after the initial amount, this is T2. Okay, we call it, Q2, not T2. Okay, so 10 times 0.87 square, see, and that 2 right here results in a square. But now we start noticing there's a repetitive pattern that the decay factors keep being carried over and carried over. Okay, and so this final expression right here, 10 times 0.87 cubed, we can think of that as this is the quantity when t equals 3. See, t equals 3, so we have Q3, but Q3 is calculated according to this rule right here, according to this formulation. So 10 times 0.87 cubed, okay, t equals 3, we got a cubed here. Okay, and so now that's why I can be firm that in t days, after about 3 observation steps right there, right, we can see that I can formulate that the quantity in t days will be 10 times 0.87 raised to the t power. Okay. So now again I observed this is an exponential function. This is what I'm seeing here is an exponential function. Okay. Q of t equals 10 times 0.87 t. All right, so now really 4 problems in a row that I have explained back to back. Like there are 4 problems in a row that I have explained back to back. So some problems, like those problems from 1, 2, and 3, like that. Okay, those are a problem where the quantity was growing, but in the end, it's a changing quantity by a proportion. The proportion is indicating by the rates here. The problem we just now finished is again the problem where the quantity on its own is changing. And it's changing by a proportion, and I also have to mention that it's changed by a proportion periodically, on equal periods of time like that. Okay, so now once you have seen enough generality, I believe we don't need to bring up that problem number 5 right there. But even though at some other in some other problems, some other places throughout this lecture, I will also bring in that problem number 5. But right now at this end right here, you have already seen enough understanding. Okay, you have already seen enough generalizations like this. So some process is gaining or is growing on its own, but some other process is losing on its own. So process that's growing on its own, we call that it's a growth. Okay, and those are processes that's losing its own, we call that it's a decay right here. And so that proportion indicating how much it's changed. If it's a growing problem, we call it's a growth rate. And if it's a problem where the quantity is losing on its own right here, we call that it's a decay rate. All right. All right, so now after seeing enough illustrations throughout the 4 problems, and as I said earlier, I didn't have to go through all 5 problems yet, and in some other examples I will be able to bring in problem number 5, but just like how I was explaining in the beginning of the lecture here, I'm gonna be quite circulating around these 5 problems. So whatever we have done to the first 4 problems are not really the end of the 4 problems yet, and we can keep coming back and dig out more information and more information. But now at this point, it's a perfectly a good place to bring in, to put side by side the result we have formulated for the 4 problems there. Okay, at least we have, for each of the 4 problems that we have done, we have come to a final function, a final modeling function. So allow me to put on my board here all of those 4 problems. Okay. So, right under problem 1 right here, For problem 1, this is what we've come up with. So the quantity there was a population. So population in terms over t years, population in t years, this is what we have already formulated, okay, was will be 25 millions, okay, multiplied with 1.045 to the t. All right, so again, the function that we've formulated at the end of problem 1 that I've sketched down earlier, the population, I notated that as a p quantity right there. So the population at t time, so the population of utopia at t time, at t years later. So t was measured in years, and then that was 25 million at start. So this was what I call p sub 0. Okay, the initial amount right here, and then that 1.045 was called the growth factor, and this 0.045 came out from the growth rate being 4.5% each year right there. So R was a 4.5%. Okay, and then the p sub 0. Okay, the initial amount right here was 25 millions. Okay, and so we've had these information right here that was given in the problem, and we call that the growth rate. Okay. Okay, and then this is initial amount, or the initial population amount for the population. Okay, so that was a function right here. And so now in the next one, problem number 2. For problem number 2, I came to P of t. I also used P of t as to indicate the quantity, the population, because problem number 2 we study about the population of bacteria. Okay, and so it was 11,000 multiplied with 2 to the t. Okay, but so we had a growth rate here again. Our growth rate was 100%. Okay, and this was a growth rate. Okay, and then 11,000 was our initial amount. So this symbol at this point is understood as the initial amount. Okay, so P sub 0 is 11,000. Okay, and then now after putting the two problems here together, this is initial amount. Okay, so now after putting the two problems together, we already noticed the t here, okay, was time in hours. Okay, so there's always a time variable. There's always a time variable in any of these functions here. See, time variable, time variable. Okay, but time here in problem number 2 was in hours, whereas time here, okay, t is again time, but in years. Okay, because it takes some number of years for a population of human to grow, for a population in a country to grow. Okay, and then we came to problem number 3. All right, so problem number 3 right there. Okay, so here I didn't call that P, but I call that the quantity. So because it's instead of thinking of the quantity as a population, I think of the quantity in the problem number 3 as a quantity, as an amount, right? It's money. It was financial math. So So that quantity now I call it Q of t, and a quantity, and we finalized that. We formulated as a function. We formulated that as a function of 4,000. That was our initial amount right there again. Okay, so 4,000 times 1.07. Okay, 1.07 raised to the t again. Okay, and so again, R here, we use a growth rate. So R is 7%. And yes, that was our growth rate. Okay. And I also mentioned, I also should have mentioned that in the problem itself, when I was working through each problem, each one of these problems, I didn't even mention using a variable for the R here. But now it's time to to finalize all that. The idea earlier, I only called that the growth rate, okay, or the decay rate later on. Okay, but now we can assign those rate as a letter R, as a variable R as well. Okay, so now the growth rate for this problem 3 was a 7%, and then we're looking at the p sub quantity, initial quantity Q sub 0 in this case was that 4,000. Okay, we got $4,000 that we brought in the bank at that initial moment, and yes, time is the t variable here is time, and that was time in years again. Okay, that's how a lot of times the banking system works. Okay, we will earn interest over the years. All right, and then just now, and then we came to problem 4 here. But now the generality between the first 3 problems, problems 1, 2, 3, right there, those are all the growth. Right there. It was a growth process. But now problem 4 that we have seen just right before this, right here, then the quantity. We have a quantity right there, and we came to having 10 times 0.87 to the t. Okay. And then so we have a rate here that was a 13%. Okay, that was a 13%, and then this was for this problem it was called a decay rate. Right, it's a decay rate, and then the quantity at start, I called it Q sub 0, and that was 10. Okay, and then t is the amount of time, but in days right there. All right. So now putting 4 problems here together side by side on the board right there. That's problem 1. They all have, so once again, I just want to reinforce that they all have those major characteristics that I pointed out. It's a changing quantity. It's a quantity that's changing. That's why we have to come up with a function. So once we come up with these functions, it will help us. Any one of these functions will help us predict what's going to happen in some years later. What's going to be the population like in some many hours later after the initial times. Like that. Okay, so it's a quantity that's changing, and then they all have an initial amount given. Okay, and they all have some kind of rates given, and that rates once given, it's a fixed proportion, it's a constant proportion. Okay, and the problem can be a growing problem like this, like problem 1, problem 2, and problem 3. Okay, problem 3 is also a growing problem. The quantity is growing, but then in some other problems, the quantity is changing. It's changing by a rate, by a proportion, by a constant proportion in each time period. And so I just now use that term precisely, in each time period. See, that's why that was ordered. That reason why I wrote it down and I nailed it down clearly. Like say in this problem here, time was in days, so it's each period here is a day. A day is one period. The next day is already the next period. Some in the earlier problems there is a time in years, so 1 year is one period. The next year is a t equals 2. The next year is t equals 3, whatever. Okay, and then in some other problems the t is in hours. That means 1 hour is one period. Okay, all right. So now some problem is a growth process. Some other problem is a decay process right there. Okay, some problem is a growth process. The quantity is gaining its own naturally or automatically. And then in some other problem, it's losing itself, so it's a decay process. But so now if we're having a closer look, and I also brought this up at the end of problem 1 already, but only briefly, so now it's time to formulate all of that. So look right at the final function right here. Eventually it all came down in the form of an exponential function. All right, so now in this narrow space of my board right here, allow me to write down some generalization that I have seen right there. See, it looks like so far it's always going to be some, when it comes to modeling any of these quantities that's changing by a fixed proportion in each period of time right there. Okay, then we can always bring it down to the form of some exponential function, a to the t right there. A to the t, this is a, base a to the t, exponential function. Okay, and multiply with a coefficient, So c times a to the t. Just like that in problem 3 right there, the function that eventually we derived, the function that we formulated, and then we use this function to model the rest of the process right there. It's an exponential function. See, a to the t, this is a right here, a equals 1.07 to the t, and then we have a constant coefficient, just like that. All right. And then right here in our problem number 1, the population over time, over years, is growing. That population of utopia was growing or is growing at that can be modeled or growing accordingly to this function right here, where it is again c times a to the t, a constant coefficient, multiplied with a to the t right there, exponential function. And again, this is an exponential function. This is how I can now say that this is the reason why we need to study about exponential functions, because exponential functions exist in a lot of applications out there. As a matter of fact, quite an unlimited number of applications out there where we can realize that there's an exponential function existing and can be used to model or predict our population size or our quantity size at a different time instance. Yeah. Okay. And now even a little more specifically, let's look even closer and more closely into the form of any of these. In problem number 4, let's look right at that coefficient c right here. That coefficient c, so now we're all clear that any one of these problems, either a growth or a decay process, they are going to have to go by an exponential function. So clearly now exponential function exists because, or we study exponential functions because there were these problems where exponential function is the best place to model it. But now if we're looking even further, then any one of these exponential functions we have derived, it's in the form of a constant coefficient times the base a to the t. But now even more closely, or even into a closer look right here, then the constant coefficient in front of the exponential term is, so here it's a 10, okay, and now and here it's that 10. All right, and then here it's a 4,000 for problem 3 right there as a constant coefficient here, and that 4,000 came out from the initial quantity. Okay, that 10 right here as a constant coefficient in our final function, that 10 came out from the given initial amount. So this is given initial amount, that was given initial amount, and just like that, c times a to the t, our a is 2, so 2 to the t, but the constant coefficient here came from the initial amount. All right, and just like that, now I've had this here long enough. Let me erase that because now I want to underline that with red ink right here. This constant coefficient, 25 millions, it came from, where did that come from? It came from this 25 millions given as initial amounts. So initial amounts are always given, a lot of times given. I shouldn't say always, but a lot of times given. Okay, and then once it's given, now back to the form of the function right here, we can even see more. We can even see more generalization. Okay, so it's not just any c out there, but generally speaking, it looks like if we call our quantity a function p of t right here, and yes, it's a to the t multiplied with some coefficient. That coefficient is the initial amount, the amount that we're starting out with. Okay, and I do admit I said the word, given, but it's only a lot of times, not always. There will be problems where we have to find out how much initial amount that was. Okay, but one thing as a rule to be always right here, it's always the initial amount, always the initial amount multiplied with some factor raised to, or some base raised to an exponent. That's the rule right there. So it's always going to have that constant, and that constant coefficient being the coefficient. Being the initial amount. That's what it is. All right, and so now let's even put that further. Okay, so how about let's for now focus to the growth problem. This problem where money was growing, 1.07. 1.07 as the A. So in this problem right here, our A to the T, so that A, the base A here came out from, see, throughout. So if you have to, please do it, but look back at the earlier part of the video, the part where I specifically derived this problem right there. See how we got this base 1.07. So base here is 1.07, but it really came from 1 plus 0.07. And 1 plus 0.07 is indeed, now to underline that, this 0.107 came out from that, the growth rate. So the base A in our exponential function, for this problem 3 at least, came out from 1 plus the rates, the growth rate of the growth rates that comes with the function. Okay, in that problem it was given, and a lot of times also it will be given, but as a rule that will always happen, whatever growth rates, whether you know it or we don't know it, but there will always be a growth rate. 1 plus the growth rate, but of course write that in decimals like how I was doing that in the live problem earlier. Okay, so let's see if this was true for the other problems. So these two problems here, in these two problems, the quantity was growing, going up, getting size right here. So the base is here, 2 to the t. So yes, the base there is regarded as a base A right there. So it's a 2, but 2 was, throughout my work, I explained that as a 1 plus 1. 1 plus 1. So we increase by 100% every hour. Doubling means that we increase by 100%. So from whatever the previous period, I'm going to add 100% of that, okay, to itself right there. And that's why we resulted in this rate right here being a complete 1. So I'm underlining that, but it's perfectly consistent. It is exactly that 100% written in decimal form. So growth rate, so we go 1 plus the growth rate to get the base of our exponential function. All right, and so is that also the same? Was that also the same with this problem right here? See, the A is right there. That's A, 1.045. So A here is throughout my work. And again, rewind the video if you have to. Okay, 1 plus 0.045. 1 plus 0.045. So where did this 0.045 come from? This 0.045 came from this 4.5%. It was our growth rate. It was given in this problem, number 1 right there. But so in this problem, growth rate was given, but as a rule, there will always be a constant growth rate. Okay, whether we know it or not. Some problem we have to find a growth rate. Some other problem we don't. It's given. Okay, but there will always be a constant growth rate. Okay, and that came from here, and then that becomes our base. That gave rise to our base. All right, so problem 1, 2, and 3 have all of that. The base is 1 plus the growth rate, 1 plus the growth rate. So what about that problem number 3 right here? That problem number 3. The base is here, 0.87. Okay, and I want to reserve the space here for this particular the little formula right there. So I want to write my work here. The base A for this problem number 4 is 0.87. 0.87. So it's not 1 plus. We still have that rate right here, but it really was. And if we look back at the works where I worked through the steps like that, and it's 1 minus 0.13. 1 minus 0.13. And so this was the rate right here. But see, it's minus because this rate was a decay rate there. Okay, so we, the material, the substance itself, the chemical elements itself was decaying, breaking it down, over time, right there, in each period of time, right there. Okay, and so here it was a decay process, unlike the other problems where it was a growth process. Here it's a decay process. So we're gonna go 1 minus 0.13, 1 minus the decay rate. All right, and then that's how it gave rise to this base of our exponential function. All right, so now in that way we are ready for this is not a definition, it's not and the whole lecture here, that's pretty much no definition at all. Every definition you've learned was given in the lectures before, where I talked about what an exponential function is and all that, etc., etc. Here it's all about we keep working through problems and we come out with generalizations, that's all. Maybe there are a few minor definition of symbols or explanation of symbols and notations, but those are, I may use symbols one way, other professors, other textbook authors might use symbols differently. Okay, so anyone teaching this will have to have a section somewhere clarifying about the use of notations. That's all, but there will be no new definitions, and not even theorem. Some textbooks refer to these something here and there as theorem, but I don't need to see these as we don't need to see these as theorems. Okay, so let's come up with some generalization here. In the way how I'm seeing it, let's come up with some generalization here. I already got that down right here, and it came to that a to the t times with strictly the initial amount. But it's a little more detail with the a base here, because some base it's a 1 minus the rate, some other base is 1 plus the rate right there. So we're gonna really tear it down right there. All right, so now allow me to swing over to the board, because I don't want to spend time writing it on the board, wasting your time watching my way writing it. So I'm gonna put the wording right on the computer screen right here. Okay, and so here's some generalization. All right, so what we've been doing is that we start having a quantity that's changing. So here in the way how I'm wording it as a generalization, we have seen this generalization throughout all 4 problems so far. Okay, if a quantity with an initial amount p sub 0, okay, if a quantity with initial amount p sub 0 is changed, see, in any one of the problems we have done, it was an amount and it's changed. It started out initially with some amount, and the initial amount is called p sub 0. That I indicated that. Okay. And then with that initial amount right there, it's going to change over periods of time, equal periods of time. That's why on my wording right here, I'm saying, see, if the initial amount, p sub 0, is changed by a constant proportion r, okay? Because the rate here, in each of the problem, we call it as a rate, but in the end, the rate appears to be a proportion of its current size, okay? Now, I'm using this word current size here a little loosely right here, but current size, I mean, when you're at a certain period, when you're about to do the calculation on a specific period, then, currently up to that point, the size of the population, that means it's whatever carried out from the previous the size like that. But carrying out from the previous size to this current period where you are about to calculate, we call that it's the current size. That's how I'm seeing it. Okay, and so now if a quantity with initial amount p sub 0 is changed by a constant proportion r of its current size for each equal period of time. Okay, and this is what I've been indicating earlier, that in some problems in some of the problems, time is measured in days, like right here, okay? In some other problems, time is measured in years, like this problem right here. But each one of those is a time period, is an equal periods of time in each equal period. And so we saw it earlier that in each equal period, the money is growing by this proportion. In each period, being a day for each period, the material, the chemical elements was breaking down, was decaying by that proportion of its current size. And current size means if you are at 3 hours later, then when you're about to calculate that, then currently the amount was from period 2 right there. Okay, and that's the idea. All right, so now if that's so, if see all of these descriptions right here fits with what we have been doing, then the quantity at any time t. So now generally we regard to that as a quantity p. It was the same quantity that I talked here, but initially it was a p sub 0. And now the quantity at any time t, now that's why I call it p of t right here, can be modeled by an exponential function. So any process, any quantity that's changing in this highlighted description right here can be modeled by an exponential function. So this generalization right here comes out to enforce that we will always have exponential functions existing out there serving the purpose to model these quantity that's changing according to that description, according to the description that's given on my corner of the screen like that. Okay, and now let's look even further. So this is exactly that form I wrote down on my board right just earlier. That is this particular form right here. Some quantity at t time, okay, equals p sub 0. It's p sub 0 that you're seeing on that computer screen right there, that corner of the computer screen, and multiply with some base a to the t. Okay, so that's the generalization. We have seen that throughout all 4 problems, and I really spent a lot of time. I hope viewers are not tired out of too much detailed explanation, but I really lay it down so that eventually you all see there's one generalization that lived inside of each one of those, and it's one common generalization right there. Okay, and now upon taking this generalization, there's further detail that branched out depending on the process being a growth or a process being a decay right here. Okay, so now I'm going to erase my board and write it down, because whatever on the screen there is only a generalization, just a general situation right there that, hey, the quantity is changing. But now as far as changing, some quantity is changing in a way indicating it's growing, and some other quantity is changing in a way that it's losing itself like that. Okay, all right, so in that way, now even look further into the situation. So yes, the quantity p of t can generally be modeled by p sub 0, the initial amount times a to the t, times a to the t. But then there's time when if the quantity is growing, okay? So this is exponential. And now specifically, if that quantity is growing as time goes on, then here's some correspondence right here. The a will be 1 plus the rate. 1 plus the rate. So we have seen that in problem 3. Sadly, I had to erase that. Problem 3, we had a rate. So the rate will always be indicated by a positive number. The rate will always be indicated by a positive number. Okay, but then what matters now is when we're creating the base. If in the problem the quantity is growing, if the quantity is growing in the problem, then the base of our exponential is 1 plus the rate in decimal, of course. Okay, so if the quantity is growing, then the base is found by 1 plus or now formally speaking, the function will become p of t equals p sub 0 times 1 plus r to the t. That's the basic form right there. That's the basic understanding. Okay, so it's always going to be p sub 0 times 1 plus r to the t. 1 plus r to the t. And then we call, in this case right here, if the quantity is growing, okay, the process is referred to as another bullet point. Okay, so the process where the quantity is growing on its own, the process is called an exponential, because we use exponential function to model it. So now, but it's a growing process, so the process here is called an exponential growth. This is now, ladies and gentlemen, this is now, and this is how a lot of times you hear in your daily terms, okay, in your daily life, people using the term, this quantity is growing exponentially, or we have an exponential growth. This is what it is. Okay, it's a quantity that's growing according to an exponential model, an exponential function, where we can find based on the rates and all that, and then we call that process an exponential growth. Okay, that's what it is. And so similarly, so now that's the case where the quantity is observed to be growing. Okay, and so that's the highlight. So now similarly, same function again, same quantity. If it's changing by with all that the description I've had on the computer screen earlier. All right, so now if the quantity is reducing, okay, so I always want to start out with daily term first. For daily language, we notice there's a reduction of the quantity over time. So that's why I'm saying if the quantity is noticed to be reducing, okay, or the quantity for short is reducing. If that's the case, then the base a in our exponential function, is going to be 1 minus the rate. And so just like that, the rate is always expressed. A lot of times the rate given in the problem is expressed as just as a positive rate. But then the base will be calculated as 1 minus the rate. 1 minus the rate. Okay, 1 minus the rate. And then so that means specifically speaking, our function to model the quantity changing right here is going to be p of t that equals p sub 0 times 1 minus r to the t. 1 minus r to the t. And then yes, as a second bullet right here, this process right here where the quantity is losing itself, is reducing itself, okay, the process is called an exponential decay. All right, so it's called an exponential decay. So you may call this a definition or not, but I highlight the term here. I didn't really intend to treat these, I'm writing on the board as an exponential, as a definition of what exponential growth or exponential decay means. I just want to clarify for any one of you, because long before you enter this lesson, you must have heard about people out there in your daily life talking about, hey, there's an exponential growth here, there's an exponential decay here. This is now where you understand exactly what that is. Okay, so there you go, exponential decay, or there's exponential growth here, exponential growth and exponential decay. All right.